Okay, let's examine 4.3, which has to do with logarithmic functions. And we're going to start out by considering the inverse of an exponential function. So in an earlier lecture, or video I guess is what they are now, we're considering an exponential function, f of x is equal to b to the x. And I asked the question whether that function crosses its horizontal asymptote. And we know it doesn't. And I asked how you might find an algebraic way to solve that, or some other method other than just looking what happens to b to the x power as x gets increasingly smaller. And in order to answer the question algebraically, you try to solve the equation 0 is equal to b to the x. And we're actually going to talk about that a little bit at the very end of this lecture. It's part of what we actually do in this class that's not quite included in the text. But the more advanced you get in math, the more it becomes necessary to put a lot of puzzle pieces together and understand concepts and the logic behind concepts as much as it is to do the algebraic manipulation. For the most part, we really concentrate on the algebraic manipulation, but I also want to focus on the mathematical reasoning part. And that's what really is the engine of math, of course, in my own view. But let's go back to here. So let's consider the graph of f of x is equal to b to the x. We know it passes the horizontal line test. We know it's an increasing function if b is greater than 0. And we know it's a decreasing function if b is between 0 and 1. So we know it has an inverse. And to find the inverse the normal way, we would replace f of x with y, and we would write y is equal to b of x, and then we would switch the x with the y, and we would get x is equal to b to the y. So y is the exponent that we need to raise the base b to in order to find x. And this value y is actually got a name. It's called the logarithm to the base b of x. And we symbolize it by log, and down here in subscript is the b, and here we have our value x. So we actually read this, I say right here, this will be the way I'm almost always going to say it. I'm going to almost always say it the log to the base b of x. Some people will say the log of x to the base b, or the base b logarithm of x. All of those are the same. So here are the interesting parts. So let me bring up my sketch pad here. So I'm sure I'll want to write something eventually. So here is the definition. So this is really important that you get this line right here where I'm pointing to with my mouse. So this is true for all real numbers y and positive numbers b and x, with the exception that b cannot be 1. The symbolism log to the base b of x equals y is exactly the same as x is equal to the base b to the yth power. So that's going to be really important, this equivalence in meaning between these two statements. How I always remember to do it when I was learning this is I would just take b and raise it to the power, because I would remember that b was my base. And for that reason, I actually changed the variable, or the constant b, in my notes from an a, what the book has, to a b, so you'll remember that that is the base. And it's natural to raise the base to the power y, And then I remember this relationship is one of equals. So b to the y equals x, or x is equal to b to the y. These two symbols, what's in cyan or light blue and what's in yellow, are exactly the same. And that's going to be the most important thing. Moreover, let's make this really, really clear as well. If, I don't want red, I don't think, we'll go to yellow, the standard. If f of x is an exponential function, then we know its inverse exists, and we normally write it as f inverse x. But for historical reasons that I cannot tell you, I don't know them, we don't write f inverse of x. Instead, we write log to the base b of x. So this is the inverse. So literally this part right here is what we write rather than f inverse. And probably one of the reasons we write something else, I know the guy who came up with logs. The guy's interesting. If any of you are interested, I should have looked this up. Napier. He was a very interesting guy that lived in England in maybe the 16th century, and he was obsessed about religion and all of this stuff and predicted the exact, I think, date and time of the end of the world. Of course, he was dead wrong, but he also came up with logarithms, so he did something good. So at any rate, this is the name of the inverse function of f of x is equal to b to the x. And again, I think one of the reasons that they use log, I don't know about log, but the inverse function depends upon the base, and this is the way that we can shove the base in there. So with this said, I just kind of remind you for historical reasons, we don't use the f inverse notation for the inverse function of exponential functions. We just use log to the base b of x, or if you like, log to the base b with x in parentheses is this kind of keys you in that x is our input function, is our input. So here is the two things we're going to use. Another, definitely put this down to know. Because of what we said, the two following things hold. So we have, and I'm not going to derive it for you. I could, but this is, I'm having a feeling this is going to be a little bit of a long video lecture. So I'm just going to take this on faith right now, or take it by my authority and the authority of the book, that these two hold. The log to the base b of b to the x is equal to x. Now that's not difficult, is it? Because of what I just said, we already know, let me just keep this here, we already know that log to the base b of x equals y implies b raised to the y is equal to x. This is the same thing as saying b to the y is equal to x. So here, let's look at this. It makes it absolutely clear. This means b to the x power is, of course, equal to what's in parentheses, b to the x. So that makes complete sense. And the next one, which seems a little bit odd, is the following: is that b raised to the log. So remember, log to the base b of x is always a number, so it makes sense to raise it to this number. is going to be equal to x. This is the one that is probably a little bit unfamiliar for you, and we're not going to use it. I'm going to put a little star right here. We're not going to use it in this particular lecture, but we will use it when we start solving logarithmic equations. So all of this is true for all b greater than 0 but not equal to 1. I already stated that at the very beginning, but I want to re-emphasize it. So here is really a good way to kind of get used to the pattern relationship between exponential and logarithmic forms or functions. So here I have, let's look, log to the base 2 of 8 is equal to 3. So if I take 2 and raise it to the third power, I get 8. That's the exponential form. Log to the 1/2 of 16 is equal to -4. Means 1/2 raised to the power of -4 is equal to 16. Log to the base 10 of 100,000 is equal to 5, implies 10 raised to the 5th power is equal to 100,000. Log to the base 3 of 1/81, 1 over 81, is equal to -4, implies 3 raised to the -4 is equal to 1 over 81. Log to the base 5 of 5 is equal to 1, implies 5 to the first power is equal to 5. Log to the 3/4, so notice our bases do not have to be integers. They can be any value greater than 0, but not equal to 1. So log to the 3/4 power raised to the log to the 3/4 power of 1 is equal to 0, implies 3 to the 4th raised to the 0th power is equal to 1. So I went from the logarithmic form to the exponential form. You should spend some time going from the exponential form to the logarithmic form. So for the exponential form, whatever your base is, that's log to the base b. Whatever your result is your x value. And whatever your power is your y value. So this is log to the base 10 of 100,000 is equal to 5. Things you definitely need to get these relationships down. And I think you've got several homework problems, or at least the first 3, that require you to do that very thing. So now let's use these properties, and we're going to solve some really simple logarithmic equations. Now, the solutions to these equations here are going to follow pretty much straightforward from the definition. We're going to get really into solving and applying logarithmic equations later on in another lecture. So let me check, how am I doing here? That's pretty good. So let's do 2a. We're going to do all of these. So if you feel like you know what's going on, you can fast forward through the video. That's one of the bonuses of making the video, is I can go slower for those who need it. And for those who don't, you can fast forward. So we want to solve for x. So that's fine. It's a kind of an odd equation because, look, x is down here. We're trying to find the base. So the first thing we do is we write it in the equivalent form. This implies x to the third is equal to 8 over 27. So remember, that's that move. You've got to be able to make that move. X to the third is equal, this is it equals this number. So here I've translated it to its equivalent form. So now we know how to solve these types of equations. So what I want to do is write 8 is a power of 3 and 27 is a power of 3. But 2 to the third and 3 to the third, 2 to the third is equal to 8 and 3 to the third is equal to 27. So that gives me over here x to the third is equal to 2 thirds to the third. So hence x is equal to 2 thirds. So basically x to the third is equal to 2 thirds to the third. X has to be that base. Okay, so let's do another one. Not too bad. Really different though. I know it's got to look really different unless you've done logs before, and some of you may have. My first encounter with logarithms was as a kid. I was way into astronomy, and I got every book I could get on the moon, because I was into the moon. And way back then, it was before, the book I had was long before handheld calculators. Yes, they do exist. And they use logarithms to calculate large numbers. And they also use what's called, I forgot, some kind of ruler-like thing. I'll think of it here in a second. So I had no idea what log was, and I just memorized all of these things: log this, log that, log this, log that, having no idea what log meant mathematically, and no one I knew could explain it to me. And then, of course, I finally got to take math in high school, and I understood what log was. So our first move here is we're going to translate this into what it means. This means 4 raised to the 5 halves power is equal to x. So I'm going to rewrite this. I'm going to concentrate on this side over here. I'm going to write this as 4 to the 1/2 power raised to the 5th, and that's equal to x. But 4 to the 1/2 power is the same thing as the square root of 4, and that's raised to the 5th. But the square root of 4 is 2, and that's raised to the 5th power, and here that's equal to 2, 4, 8, 16, 32. This is equal to 32. Let's go on. And the final one, this should be C. Apparently I forgot to put it in here. This is 2C. So we have log to the base 49 of the cubed root of 7 is equal to x. So again, we just rewrite this. This says 49 to the x power is equal to the cube root of 7. So what I'm going to redo here is I'm going to rewrite this. So I'm going to leave 49 alone for right now. It's going to be raised to the xth power. And the cube root of 7 is the same as 7 to the 1/3 power. We learned that a few sections ago. So that's 7 to the 1/3 power. So that's somewhat helpful. And now I'm going to write 49 as 7 squared. So I have 7 squared, which is my 49, raised to the x power is equal to 7 to the 1/3. But again, using my exponent laws, 7 squared to the x power is 7 raised to the 2x power, and that's equal to 7 to the 1/3. So in an earlier class we learned that if b raised to the c is equal to b raised to the r, then c is equal to r. Why? Because they are one-to-one functions. So this implies 2x is equal to 1/3. Why? Because my whole thing was to get the same base. So that's easy to solve for x. X is equal to 1/6, divided both sides by 2. And that's all for that page. So the next page is we're going to plot. And the first thing we're going to do is, let's start here, is I'm going to bring up, I guess, GeoGebra for this. Here we go. If I've used it more than once, I'll do the classic version. Graphing. And I'll come back to this in just a second. So we are asked to plot log to the base 2 of x. But instead of plotting log to the base 2 of x, I'm going to plot its inverse, the inverse function. So if f inverse of x is equal to log to the base 2 of x, then f of x is equal to 2 to the x. And we're going to use some of the properties that we learned earlier about plotting. So it's easy to calculate, if I am given x, to calculate 2 to the x. Just to do a few of these, you might be wondering, what about that first? So if x is equal to minus 2 to the x is equal to 2 to the minus 2, which is the same as 1 over 2 squared, which is equal to 1 over 4. So in case you forgot that, that's what's going on. Anyway, I provide you with a list of values. And that's as small as I can make it. So remember that here's the principle we're going to use. If a point x, f of x, lies on the graph of f of x, then the point f of x lays on the graph of f inverse x. That's something we did in the last lesson or before. So what that tells us is I get a table of values. So for log to the base 2 of x, if minus 2 1/4 lays on the graph of f of x is equal to 2 to the x, then the point 1/4 and minus 2 lies on the graph of log to the base 2 of x. If minus 1 and 1/2 is on the graph of f of x is equal to 2 to the x, then 1/2 minus 1 lies on the graph of its inverse, which is log to the base 2 of x. If 0, 1 lies on the graph of f of x, then 1, 0 lies on the graph of f inverse x. If 1, 2 lies on the graph of f of x, then 2, 1 lies on the graph of f inverse. If 2, 4 lies on the graph of f of x, then 4, 2, 4, 2 lies on the graph of its inverse. And if 3, 8 lies on the graph of f of x, then 8, 3 lies on the graph of f inverse. So this set of points right here are all points on the graph of f inverse x, which is log to the base 2 of x. So let's take a look at those. So my first point, I'm going to enter them in over here, is 1/4 comma minus 2. And right there we go. So let's do another point. The next point is going to be 1/2 comma minus 1. And it's right there. Let's do another one. Our next point is 1, 0. Well, I can actually add that point myself. 1, 0. The next point is 2, 1. The next point is 4, 2. The next point is 8 and 3. So if you can kind of draw a line through these, you can kind of see a smooth line going down here. And it's going to be the reflection of 2 to the x about this axis. I'm not for sure how to enter in logarithms here. Let's see, is there one? Let's just try log. Let's just try it. Log to the base 2 of x. Oh, yeah, there we go. Perfect. So there we can see the graph of log to the base 2 of x and compare it to the graph of f of x is equal to 2 to the x. So kind of cool. So that's that one. Let's get some more properties of the graph of the logarithmic function. So notice that the logarithmic function, let's just take a little look at this while I've got it here. Let's look at the red. That it doesn't have a horizontal asymptote. It grows ever so slowly. It seems like it's almost flat, but it's never flat. So it grows in value inversely proportional to the way f of e is equal to 2 to the x increases exponentially. Notice that this is the graph of f of x is equal to 2 to the x. This is an exponential function. You can see how fast it increases. And its horizontal asymptote is the x-axis. Here we have no horizontal asymptote, but rather the y-axis is a vertical one. Also, while it's on my mind, I just actually worked through these problems today, and I made several changes to the PDF of your notes, so you might want to print out a new copy of those. You'll notice some differences here. I corrected some obvious typos and changed some things. So back to here, and then back to here. So let's just look at some graphing of the exponential functions. So here is what we just want to focus, is this right here. If a point x, f of x, remember f of x is equal to y, lies on the graph of f of x is equal to a to the x, then the point f of x lies on the graph of f inverse x is equal to log to the a of x. So another way to think about it is this way. So let y equal f of x equal a to the x, then every point on the graph is of this form. X, y, that's just standard, but I have some more information about y, right? Y is equal to f of x, but I have some more information about f of x. F of x is equal to a to the x. So every point on the graph of y is equal to a to the x takes this form. Now f inverse of x is equal to log to the base a of x. Then, since this is the inverse function of f, then we have every point on it looks like this. It's like my input is x and my output becomes a to the x. It's like the input and the output is reversed. So let's look at some characteristics of the graph of f of x is equal to a to the x, and let's fill in some of these boxes. So I'm going to make this a little bit smaller so we can get everything in. So notice that this is characteristics of the graph of f of x is equal to a to the x. So this is a little box I got from section 4.2, I believe. So the points minus 1 and 1 over a, 0 and 1, and 1 comma a are on the graph. On the graph of f of x is equal to a to the x. This is the exponential function to the base a. So I've kind of changed things around now. The book uses the variable for our base as a. I started out using the variable b because b stands for base, but now that you've got it in your head, just know that a and b are the same constants. So they're constant values. They're not variables like x, they're constants. So if a is greater than 1, then f is an increasing function. If a is between 0 and 1, then f is a decreasing function. The x-axis is a horizontal asymptote. The domain is minus infinity to infinity, and the range is 0 to infinity. So now we're going to consider the questions based upon the inverse function of f of x is equal to a to the x. In other words, log to the base a of x. So you should try to answer these on your own before I actually supply the answer. And we're literally going to take them from this table. Can I not make this any smaller? So the points blank, blank, and blank are on the graph of log to the base a of x. I can make this smaller. Well, the points, if minus 1, 1 over a is on the graph of f of x, then the points 1 over a and minus 1 are on the graph of log to the base a of x because it's the inverse function. Similarly, if the point 0, 1 is on the graph of f of x is equal to a to the x, then the point 1, 0 is on the graph of log to the base a of x. If the point 1a is on the graph of f of x is equal to a to the x, then the point a1 lies on the graph of log to the base a of x. Why am I doing it this way? So you only have to memorize one of these tables. And once you have one of these tables memorized, you can make the corresponding inferences about the inverse function. So that's one. The next question I give you is, I just tell you this a fact. If a is greater than 1, then log to the base a is an increasing function. If the base is between 0 and 1, then log to the base a of x is a decreasing function. The blank axis is a vertical asymptote. Well, we already figured that out. There is no horizontal axis. The y-axis is a vertical asymptote. Up here we have the x-axis is a horizontal. Down here we have the y-axis is a vertical. The domain of log to the base a of x is blank and the range is blank. Remember what happens to the domains and ranges for inverse functions? So if the domain of the exponential function f of x is equal to a to the x, and the domain is minus infinity to infinity, and the range is 0, 0, then the domain of log to the base a of x is 0, infinity, and the range is minus infinity to infinity. These are the types of questions you might find on your next Canvas portion of the exam. I'm just thinking about it. So here we have some algebraic properties of the log function. And this proof right here is actually given to you in the book. And normally I would go over the proof with you. But I'm not going to do that because I have another proof that I think is more interesting and more informative as far as proofs go that I'm going to present at the very end. So we're just going to take the following conclusion to the proof. The log to the base a of a product of two factors, x times y, is equal to log to the base a of x plus log to the base a of y. So, interesting. That means if I have the log to the base a of the product of two numbers, then that becomes log to the base a of the first number plus log to the base a of the second number. So in a weird way, this allows us to take multiplication and turn it back into addition in a very weird and interesting way. And these following properties are really important properties of logs. So this is for all x greater than 0, all y greater than 0, a greater than 0 but not equal to 1. Log to the base a, for this is any base whatsoever, as long as it's greater than 0 and not equal to 1. Log to the base a of x times y is equal to log to the base a of x plus log to the base a of y. The quotient property. We're going to be using these properties in just a second, so you might want to pause the video right now and make sure you have access to this table or you've written it down. So log to the base a of x divided by y is log to the base a of x minus log to the base a of y. Why is that? Well, you might actually intuit, whoops, I don't want to do this. You might actually intuit that x divided by y can be turned into a product. It's equal to x to the y raised to the minus 1. And intuitively, you might actually realize that's where the negative, the subtraction comes in. And if so, you were correct. Here's another one we're going to use all the time, constantly. Log to the base a of x raised to the power r is equal to r times log to the base a of x. So log to the base a of 3 to the 5th is equal to 5 times log to the base a of 3. That's the power property, quotient property, and product property. Log to the base a of 1 is always 0, because a to what number? A to what power gives me 1? A to the 0th gives me 1. And log to the base a of a is 1. Those last two properties aren't so astounding or difficult. So here we have some things to do. So we're going to do every last one of these. And they're not difficult, but in order for you to understand what I'm doing here, you really need to have those properties in front of you. And in particular, the book will sometimes give a few answers that it's just particular to the book. There's various answers here. In this particular grouping, it's not so bad. So this is number 5A. And we're going to start out really simple. I'm going to get my notes here because I want to make sure I'm getting the property names correct. And that's precisely what I don't have memorized. I have the property and how to use them, but the names I don't know necessarily. So I want to have my notes here so I can name them by the correct name rather than going, I can't remember. Because we don't use the names, we just, when we're actually doing this on our own, we just use the property. So we want to simplify these. Let's see what we're asked to do. We want to use properties of the logarithm to rewrite its expression. Assume all variables represent positive real numbers. And basically, just assume the variables and everything about them, make everything work out. So the first one's going to be pretty simple. I'm going to have, I got to make it bigger than that, log to the base 6. I really hate the fact that they're using all of these different bases. That's okay. Log to the base 6 of 7 times 9. So I'm going to use the product property. This is equal to log to the base 6 of 7 plus log to the base 6 of 9. So look at the product property of logs and make sure you're okay with that. Now we're going to do number B. We're given log to the base 9. And if you want to write this in parentheses, you can, of 15/7. So by the quotient property, this is log to the base 9 of 15 minus log to the base 9 of 7. So again, go back over and look at the quotient property and make sure you're okay with this. Now let's look at C. Log to the base 5 of the square root of 8. Well, the first thing I'm going to do is rewrite the square root of 8 so that I get an exponent. So the square root of 8 is the same as 8 to the 1/2 power. Now I'm going to use the power property. The 1/2 is going to come out here in front. And I'm going to multiply 1/2 to log to the base 5 of 8. So make sure you understand that this is an application of the power property. Okay. They get more hairy as we go on. Not bad, but got to be more careful. What we're going to be doing now with 5b, this is 5, exercise 5b. It's not 5b, what am I saying? It's 5d. So we're going to look at log to the base a of the cubed root of m squared. So I want to use the power property. So I'm going to have to write the cubed root of m squared is a fractional power. Let me erase some of this. So this is going to be to the 1/3 power. Make it a little bit finer. Well, now I'm going to use, again, exponent properties. That's equal to log to the m raised to the 2/3. How do I get 2/3? Because 2 times 1/3 is equal to 2/3. And that is a exponent property. And now I'm ready to use the power property. So this is equal to 2/3. That's to the base a, log to the base a of m. So not so bad. So definitely make sure you understood that. The only real thing is remembering that the nth root of b translates to b raised to 1/n. So the cube root of m squared is my base is m squared raised to 1/3. And then I use the property, the power property of, I think, exponents to get to this form. I need some more room. And let's do 5e. So we have log to the base a of m times n times q over p squared t to the 4th. So let me just get a whole bunch of room here. Make this fine. Well, by the quotient rule, this is log to the base a of the numerator, which is m times n times q, minus log to the base a of the denominator, which is p squared t to the 4th. Let's go over here. But log to the base a of m times n times q is equal to log to the base a of m plus log to the base a of n plus log to the base a of q. And the same thing over here. The log to the base a of p squared times t to the 4th is log to the base a of p squared plus log to the base a of t to the 4th. So I'm getting closer. And this is all going to stay the same. And I don't know how to cut and copy using this particular program. I don't think you can. There's probably a better one out there I could use for Linux even, but I've learned how to use this one, so I'm sticking with it. So I'm going to simplify this and this using the power property. So this is log to the base a of p squared, so that's the same as 2 times log to the base a of p. And over here, this is log to the base a of t to the fourth, so that's 4 times log to the base a of t. So the final answer is log to the base a of m plus log to the base a of n plus log to the base a of q minus 2 log to the base a of p plus 4 log to the base a of n. Okay, not so bad. So we're going to do some more. So we've gone one way, we're going to go back. So now we're going to use these properties in reverse. Whenever you have equals in math, they almost always ask you to do them in reverse. Although that last one, number C, is a doozy. So, and the answer I get is slightly different from the answer the book gives you. And I'm not for sure why the book does not give you the answer I give, given the fact that they're always wanting you to rationalize denominators. But the answers are equivalent. So we're given log to the base 3 of x plus 2 plus log to the base 3 of x minus log to the base 3 of 2. So I'm just going to put parentheses around here. So the product property gives me log to the base 3 of x plus 2 plus log to the base 3 of x is the same as log to the base 3 of x plus 2 times x. And this is minus log to the base 3 of 2. Not done anything to that. But now I can use the quotient property to write this as log to the base 3 of a fraction whose numerator is x plus 2 times x and whose denominator is, literally that's just 2. Yeah, that's just 2. That's all there is. So that one wasn't so bad. I guess you're all saying, are you kidding me, Kent? That's from hell. But, okay, listen, after chapter 6, we're going to be doing just 3 more sections. We're getting close. So we have 2 log to the base a of m minus 3 log to the base a of n. And the first thing I'm going to do is I'm going to take care of these multiples. And I'm going to use the power property. So that gives me log to the base a of m squared. So the 2 moves and becomes an exponent here. And this is, I'm going to use the same property here, minus log to the base a of n cubed. Now I'm going to use the quotient property. So this is going to give me log to the base a of m squared divided by n cubed. So again, that was not so bad. The next one's rather long and involved, but let's just do it. What I'm going to do is I'm going to write it down here, and then I'm going to give myself the full space. So this is 6c. And I have 1/2, and since the base does not matter, I'm just going to drop it, and I'm just going to call it to the log. And in the next section, we're going to learn, that's supposed to be 3/2, we're going to learn that log without any base, the base is understood to be base 10. But I just am tired of writing these bases down. Okay. So again, I'm going to group these in parentheses. So you can kind of see the quotient rule being used at some point. So I'm going to simplify this part right here. So the first thing I'm going to do is I'm going to change that as log m to the 1/2 power, because the factor in front comes up and becomes a power, plus log of the 2n, and that's my new base, and it's raised to the power of 3/2. All of this is in parentheses, and it's minus log times m squared over n. So the next thing we're going to do is use the product property right here. Is that what it's called? I just moved my back. Yeah, product property. So I'm going to simplify this part right here. So that's equal to log of m to the 1/2 power times my base is 2n to the 3/2 power minus log to the m squared over n. So what I want to do here is I want to write both of these to the same power. So still I'm going to work on this. So that gives, I'm just going to work on this part again. So this is log to the m to the 1/2 power times 2n cubed to the 1/2 power. So just verify that 2n cubed to the 1/2 power is the same as 2n to the 3/2. Why? Because 3 times 1/2 is equal to 3/2. It's that exponent property. So you really need to know your exponent properties here. And of course, this is minus log to the m squared over n. Now I'm going to rewrite this again. I'm still working on this. I'm not ready to use the quotient rule yet. That's equal to log of the m times 2n cubed, all of which is raised to the 1/2 power. Because remember, a to the 1/2 times b to the 1/2 is equal to a times b to the 1/2. That's the property I'm using right there. So you might have to go back and review. And again, I still have my minus. I've not done anything with this down here. log to the m squared over n. So what I'm going to do again is simplify what this is over here. So this is log. Now you see why I didn't want to write to the base b all the time. So this is log to the m times, so I'm raising 2n to the third power. So 2 to the third power is 8, and that's n cubed, all of which is raised to the 1/2 power. And it's going to be log m squared over n. So that's going to be equal to, now I'm going to use the quotient property. M times, I'm going to put the 8 out here, m times n cubed, this part right here, raised to the 1/2 power, I'm taking the log of this, divided by m squared over n. But that's the same thing as log to the square root of 8 times n squared times m times n. I'm just changing, I wrote n cubed is n squared times, maybe it's, you're fine with this, n squared times n is n cubed. There's my m and there's my 8. And this is over m squared over n. So now I'm going to simplify what's under the radical. So this is still, again, this is laborious, but since we're on video, you can fast forward if you want. 8 is equal to 4 times 2 times n squared times m times n over m squared over 2. We're almost there, folks. That's equal to log, and now I'm going to simplify this. I'm going to pull out from underneath the radical, the square root, any perfect squares. So n squared is a perfect square. The square root of n squared is n, so it's going to get pulled out. The square root of 4 is 2. So it's going to be the log of 2n. And what remains under the radical? 2 times m times n. All of this is over the square root of m squared n. So that's equal to log. And I'm going to cancel out factors of 2. I'm losing my mouse here. I'm going to cancel out factors of 2. Or factors of n, sorry. I went to change the color and I didn't change the color. So the end result is log of 2 times the square root of 2m n over m squared. And that's our answer. Now if you look at this problem in the book, their answer is not going to look like this. They literally have the log of something all under the radical, and I'm not understanding that because they always ask you to rationalize the denominator. This has the denominator rationalized. And the answer I give you here is equivalent to the answer they give you. So I don't know how that's going to work out in your My Math Lab homework. Okay. One last thing, and then actually after this I'm going to terminate the video, and I'm going to start another video on the very last page of this that has to deal with the proof. And those will also deal with questions on the Canvas portion of your next exam. So you can watch this at 2 different occasions. So this seems almost impossible what they're asking us to do here, but it's a really interesting trick that we use computationally all the time. So they tell you that the log to the base 10 of 2 is approximately equal to 0.3010. So we want you to use that fact to approximate each logarithm without using a calculator. Now this is something you might very easily find on a Canvas exam. So this is 7a. So log to the base 10 of 4. Well, that's equal to log to the base 10 of 2 squared, because 4 is equal to 2 squared. But using the, what is the name of the property? Power property. That's the same as 2 times log to the base 10 of 2, which is approximately equal to 2, and the value of log to the base 10 of 2 is given to be approximately 0.3010. So that's approximately equal to 0.6020. So that's not so bad. And then they hit us up with 7b, which I even had to think about for a second. Because 5 is not a power of 2. What do? So we're going to use this other property. Recall that log to the base 10 of 10 is equal to 1. Why? Because 10 raised to the first power is equal to 10. So this is going to be a fact that we're going to use here. So I'm going to rewrite 5 as 10 divided by 2. And hence, log to the base 10 of 5 is equal to log to the base 10 of 10 halves, which is using the quotient rule, log to the base 10 of 10 minus log to the base 10 of 2. And here we get to use this fact, log to the base 10 of 10 is equal to 1, and we were told that log to the base 10 of 2 is approximately equal to 0.3010, so that's approximately equal to 0.699, or if you want, you can say it's approximately equal to 0.7. So that's it for lecture on section 4.3. I will do another section on the last page that's coming up, mathematical reasoning, and it'll be a very short video, but I will upload those separately.